just a little bit introduction about me. I am Jianshen. I am the PhD student from UCSC Cruz, and I'm pretty excited about the workshop, Eusocial storage workshop today, because we got a really great list of speakers. And the first presentation will be talked by me, and in the presentation I will introduce the Eusocial storage devices and then my kind of my research plan for the project. And followed by that, we will have Nidish from Kioxia and Jason Molgaard from ARM, and also have Philip Kufeldt from Seagate, and have Pankaj Mehra from Samsung, and just pretty excited to hear from them. And so we can just start to go ahead and play my video.
Okay, great. I'll get started. Sorry, I'm taking one. It's taking me one extra second. Hold on one second.
Hi, good morning. I'm Jianshen. I'm a PhD student from UCSC Cruz, and today I'm going to talk about use of storage devices. My advisor is Carlos Matson. In this presentation, I would like to start with the introduction of use of storage devices, the background and motivation of it, and especially how different motivators that eventually lead us to this idea. And followed by that, I will discuss my research plan for this project, including the benefits, quantification, uses of storage architectures in the network. And I will also discuss some of the challenges that we may have along with these items. For the background and motivation discussion of uses of storage devices, I will follow this diagram block by blocks. As you can imagine, the problem starts with the big data. More and more data are generated by different clouds, edge data centers, and all kinds of endpoints, for example, IoT devices. In an IDC report published in 2018, the size of the global data sphere would reach 175 zettabytes by the end of 2025. While storing data could be a problem, it actually created a great opportunity for different companies and own of the data to get insights and make profit from the data. Therefore, the machine learning applications and the AI related applications are becoming more and more popular. As you can imagine, the AI market size relying on these applications are growing year by year quickly. And according to this report by Ondeard, published in 2019, the annual revenue created by the AI technology will reach more than $120 billion by the end of 2025. The need of processing such a tremendous amount of data requires significant CPU horsepower. However, we have seen the breakdown of data scaling. The multi-core approach hits the MNOS law, and people has already started to predict that the Moore's law is ending, and there will be no more performance improvement provided by the future CPU, probably. And the problem is that if they are brought forward, two famous scientists in this area, one is John Hersey from Stanford, and the other is David Passon from Berkeley. Both of them together predicted that the future would be domain-specific architectures. This is really true. We have seen this GPU has already taken over the tasks that require multiple parallel processes from the traditional CPUs, and the TPU is also the same case, which is developed by Google, and it has taken over those matrix processing tasks for deep learning applications from traditional CPU, and for more recently we see that the DPU or data processing unit, it is already started to taking over the network packet processing or storage request processing from the host to reduce the resource consumption of the host. While the semiconductor scaling has slowed down, the storage device performance is skyrocketing. The innovation of storage device performance with technology such as the MRAM, ReRAM, phase change memory, the VRAM, these technology actually create a solid performance engine to continuously push forward the performance of storage devices. And we have seen that the performance improvement in storage devices has already exceeded the performance improvement in CPU and DRAM. And not just that, we see that the storage interface is becoming the bottleneck of accessing storage performance from the device. With this trend, in the traditional storage architectures where the data need to move to the host computing resources, the CPU memory, in order to get the data processed, the cost of the moving the data in such a way is becoming more and more expensive. And specifically, the requirement of CPU bandwidth per device and the requirement of the DRAM bandwidth device are both increasing. To tackle this problem, the industry is starting to build computational storage devices where some of the tasks right now can be done within the device, thus effectively reducing the host resource consumption while improving the efficiency. On the other hand, in a different line, we know that application performance requirements are always changing in between different applications. But also the same application could have different performance requirements, but it is evolving. Or traditionally, when we map these performance requirement onto the hardware resources may not be such a difficulty because we only have a limited resource type to choose from. But right now, we are not just the traditional resource type, but also we have the GPU, TPU, FPGA, things like that would eventually complicate how we can map those performance requirements to hardware resources. And if we continue to continue to map this requirement to traditional server boxes that provide limited flexibility in terms of changes of performance requirement, it would inevitably result in resource underutilization and inefficient resource provision. In an IDC report, it found that in most enterprise data centers, the about 55% of the computing hour and capacity remain to be idle. And also there are about 20% of engineers reported that the efficiencies in the time required to provision compute and storage resources. To tackle this problem, industry started to about aggregating the resources where different resources types are organized in pools. The system of performance can be composed at runtime by picking up resource types from different pools. However, these two chains they basically direct us disaggregating storage devices. Without further optimization in terms of the storage architecture, we won't be able to leverage the benefits from these chains.
I think that could be a video audio problem within the playback. Should I try to play it instead?
That was my, I was just, is that my, I mean, can you hear me clearly right now?
Yes.
Okay.
So I had played it previously, but it doesn't look like there's kind of different shots within it.
Okay. Do you if you want to, do you want to play it's at 7:24 right now. Do you want to start playing it from your system and see if that's better? Okay, I'll stop sharing.
Try it. Thank you.
If you want to start it a little bit earlier to where maybe like right at 7 minutes, you may, that way you can avoid, people can hear the part that was skipping a little bit.
Just a second.
BBC report found that in most enterprises data centers, the infrastructure has about 55% of the computing power.
And we can't hear the audio if it's on.
Oh, really?
Yeah. Did you, when you shared, did you select computer audio? Stop sharing, and then if you stop sharing, and then when you reshared, make sure you select computer audio. That might solve that problem. Otherwise,
my version of Zoom doesn't support that feature.
Oh.
Okay, I'm not using,
oops. I could try mine again, or maybe if you want to start just sharing live from the that section. I couldn't, like I said, I couldn't tell if the audio, it was my system that was a problem or whether it was coming off the pre-recorded.
Okay. So you can go. You said you will try it again, and then.
Yeah. Do you want me to try it again? Okay, let's try that.
Thank you. Can you start it over?
Our idea is that to enable collective acting from storage.
I don't think it's getting better.
So let me do it in live probably.
Yeah. Sorry, what did you say?
So I can do it live presentation instead.
Okay. Yeah, sorry about that. Sorry to everyone else too.
Sorry, everyone else. Yeah. Let me bring up my slides. I continue from the same place. Can you see my screen?
Yes.
Okay, cool. So, and because of the problem that the industry has, because the resource right now have different kinds of need, it is kind of really hard to still map the application performance requirement onto so many different kinds of hardware. And so the industries start to think about the solution to disaggregate different resources in different pools, which means different hardware types right now can be organized in different pools, and such that the system, if required, the system with different performance requirement can construct the system with different performance at the runtime by picking different resources from different pools. And so with these two chains right now, basically, it kind of directs us to a direction that we would like to disaggregate the computational storage devices. Well, with this trend, with this solution, probably we're gonna move the computing resources away even further than the computing resources. And so without some kind of optimization for the storage architecture, would probably won't be able to take fully leverage the benefit coming from these two chains. And so our idea is to allow the computational storage devices to communicate with each other, and such that they can collectively fulfill some tasks that previously won't be able to do. For example, so previously with the computational storage devices, if they just rely on its own, or organized inside a single host and managed by the traditional host, and then they would just be able to do the filtering, projection, and compression tasks, things like that. But if we enable sort of the collectively behavior by allowing them peer-to-peer communicate with each other, and they right now would be able to take over those tasks such as the redundancy, failure management, and load balancing tasks that traditionally would require data traffic between hosts. And the idea really comes from the energies from like a simple ends can a simple ends cannot do anything special, but a collection of ends would be able to do some complex tasks such as building house and searching for food. And the same idea would like to apply to the storage device, and by collecting and organize them together so that they can collectively provide some function that non-individual storage devices would be able to do. And so this idea is also captured by the Metcalfe's law, where it says in a system, if the system contains n interconnected devices, then the value of the system is proportional to the got message that said I'm sorry. So the value of the system would be proportional to the square of the number of devices in the system. And so in this case, the devices would be the users of storage devices. And so in summary, the idea of the users of storage devices would be it's built up from these two chains while allowing the storage devices to be actively communicated with each other. And so this basically a diagram, the picture shows the idea of users of storage devices. And first, as I mentioned, each of the users of storage devices can actively initiate the communication with any of the other users of storage devices in the cluster through a full cross-port network. And also, different users of storage devices can be domain-specific hardware, and because they can have different function running within it, they can provide different client API, different clients, and finally, storage devices with similar capabilities can organize it into a caste, and so that they can collectively provide functions, provide some specialized function to the clients. And because the user of storage devices has the computing capability, the storage capability, and right now have the peer-to-peer capability, it could be possible to eliminate the need of host from the picture, and so therefore can effectively adjusting the host text and bandwidth mismatch problem caused by the faster storage media. So right now, getting to my first item in my research plan, which is related to the benefit quantification. And so previously we have proposed a methodology that used to quantify the benefit of offloading data access functions to storage devices. This methodology have a couple of limitations. But before, when I talk about what kind of things we want to advance this methodology, please allow me to have a quick introduction for the previous methodology. And so in this methodology, basically, we focus on the problem regarding how to compare whether the function should be running on a general purpose server or running on an embedded storage device. And so we proposed the idea to encapsulate two things: the storage media and the workload, and such that we can create a reference point for the comparison. And the result would be we develop the reference point is exactly a metric, performance metric, and we call the metric to be the media-based work unit, or MBWU. And so to understand how we use this reference point in the comparison, think about we have a workload and we try to drive the workload onto the platform, and the platform is running the function that we intended to offload to the storage device. And in this process, we can measure the throughput of the workload. But if we can ensure that the only limiting factor of the throughput in this situation is only the capability of the storage device, it is not being bottlenecked by the platform CPU or the memory subsystem of the platform, but only the bandwidth of the storage device. And so in this case, this throughput becomes a performance characterization for the workload running on the specific storage device. And so we define this throughput to be a MBWU, or media-based work unit. And so with this definition, we can now measure how many MBWUs that different platform can generate, and then we can calculate the platform efficiency by dividing the cost of a platform by the number of MBWUs that different platform can generate. And so similarly, we can also calculate the power efficiency and space efficiency. And so with this platform efficiency, we can conduct an apple-to-apple comparison between different platforms, and finally answer the question regarding whether the function should be running on a general purpose platform or on an embedded storage device. And so if you understand this is the MBWU-based measurement methodology, this methodology actually impose the following assumptions. First, it assumed that the workload is reproducible, and because we need to make sure when we measure the number of MBWUs that different platform can generate, we need to make sure that the definition of the MBWU is consistent across the different platforms. And also, this methodology didn't explicitly answer the question regarding how we can evaluate the function if the function required peer-to-peer communication. And finally, uh, this methodology is basically a throughput-based benefit quantification methodology. And while in reality, the performance of a system could be multidimensional, including not just the throughput metric, but also the latency metric and some of the other metrics, such as the availability. And so because of that, we want to advance this methodology such that it can account for not just those offline evaluation for those reproducible workload, but also can account for those online evaluation for the online dynamic workload. And also we want the methodology can specifically answer the question, and some instruction can tell us how to evaluate the function if the function reads the communication or data traffic between different value domains. And also, finally, of course, we want the methodology to be able to quantify the benefit, not just based on the throughput, but also can based on the latency and availability metrics. And also for the workload, previously we just evaluate on the key value workload with the MBWU-based measurement methodology. Even though this methodology can seamlessly apply to other data access workload, but later on for the future, we would like to measure some other interesting workloads, such as the tabular data transformation workload that probably could be accelerated by some kind of domain-specific hardware. And so in order to evaluate the performance of workload on different platforms, and we may need to chase and replay the workload in order to build a relationship for the workload performance on the different platforms, such that finally we can kind of create a model to map the relationship between different of them. And so to trace and replay the workload, it sounds easy, but actually it may comes with a couple of difficulties. First, when we chase the workload, we need to reduce the overhead of the chase as much as possible. Still, this is a hot topic in the recent research literature. And also that IO operation actually have dependencies with each other. And so in order to faithfully replay the workload on different platforms, we need to precisely capture the relationship in the within the IO requests. Even though if you can finally create a precise trace for the workload, when we get into the replay phase, we still need to consider the question regarding how fast we should replay the workload. If we replay the workload at the original speed, then we probably underestimated the tester platform. While if we choose to replay the workload as fast as possible, then probably we will it will incur unexpected high IO latency. And with this data that we collected, we can create a model for the prediction. In some implementation, try to reduce the complexity of the model by tailoring the model to some specific systems or some workloads. For example, it puts some assumption on the size of system or some specific workload. But for the benefit quantification of offloading functions to storage to the user's storage devices, we just don't want to have the assumption on the size of system or what kind of workload should be offloaded to the user's storage devices. And so therefore, we may choose to we may favor some model that is system and workload agnostic, and typically that means we would need some machine learning technologies. And so in this process, we need to choose the feature set from the data that we collected. And if the size of feature set is too small, probably the value of the feature won't be able to precisely capture the information from the data that we collected. But if we have choose the feature set is too large, then it probably would incur, it will end up with overfitting problems from the resulting model. And so, and also because we want to create a system in a workload agnostic model, and it will require us to collect the data from different system and workload configurations. And therefore, the complexity of only the data collecting phase would equals the features of the dimensions of feature times the dimensions of workloads times the dimensions of the system's configurations. And this complexity is high, and probably result in a significant time in the data collection phase. And finally, we still need to think about what kind of models that should be used to change the data that we collected. And for the benefit of availability of using embedded storage devices for storage system, we have done some work in the context of edge. And so previously, uh, uh, so the edge infrastructure usually deployed on the remote sites, and therefore we send in truck rolls to those remote sites to get the hardware, either hardware or software problem fixed, usually expensive. And so this is, and therefore it is important to improve the availability and the reliability for the edge infrastructure. And so in this work and in our previous work, we compared two different systems. One is the server-based storage system that is built with general purpose servers, and the other system is the embedded storage system that is built with embedded storage device. And because each embedded storage device is much simpler and cheaper than a general purpose server, and it makes sense to have more nodes in the embedded storage system than the number of nodes in the server-based storage system. And also because the embedded storage device essentially is independent file domains, and therefore the number of independent file domains in the embedded storage system could be much greater than the number of file domains in the server-based storage system. And therefore, our hypothesis is that the more independent file domains are file over mechanism space, the more available the data becomes. And so to verify this assumption, we create a metric called relative benefit, and it is defined by the ratio of the possibility of data loss between these two systems. And here, just need to remember that the greater the ratio, the better the embedded storage. And so for the precise mathematical model that we use in our evaluation, you can refer to the site that we have in the previous slide. But in this presentation, I just want to show what we found from our evaluation. So in general, we found that the higher resource aggregation in the server, the higher the relative benefit of embedded storage. The resource aggregation in the server could be the storage device aggregation or the computing resource aggregation. And so this result actually makes sense because if we aggregate more resources in the server, essentially it will increase the size of file domain in this storage system. And so with this understanding, we could move forward our research to study some other interesting question related to the data availability. For example, in order to achieve the similar or same data availability, what are the benefits of cost, power, and space of using embedded storage devices for storage system? And so my second piece in my research plan is related to the architectures of uses of storage. So as you know, the resource availability is the main hurdle for the architectures of users of storage devices. And so we need to look for architectures that can work with small and bound resources. And so given our research experience on Ceph, we are planning to use Ceph as our first prototyping platform and try to add some modifications that can help limit and bound resources. And also we would like our architecture that can easily accommodate and leverage domain-specific hardware. And for example, in a user storage cluster, it could involve a small set of SmartNIC that is dedicated for data transformation tasks that for the data stored on different nodes, for example. And finally, we would also like the user of storage devices not just be able to run fixed function, but also be able to run some dynamic function that is created, downloaded, or parameterized by the clients. And so for the dynamic functions, because the complexity of the function is not known beforehand, and the storage vendor may not be able to pre-allocate enough resources onto the storage devices to ensure some service level objectives. And so therefore, it is important for the architecture to provide some sort of mechanism to allow the, the offloaded function to push back to the caller. And so regarding the execution of dynamic function within the storage devices, it essentially is important to have a function execution framework that runs within the device. So currently there are two popular technologies that would allow untrusted or user customized code to be running within a sandbox environment. And so the first technology is called WebAssembly. And this technology is originally created to allow program written in language other than JavaScript to be efficiently running within the browser. And because it creates such a nice abstraction for different programming languages, and the WebAssembly community would like to extend this abstraction such that the program written in WebAssembly not just be able to call the web API, but also for those system API. For example, if you create a WebAssembly program that contains a print function, and if you compile the program into WebAssembly bytecode and run bytecode onto a runtime that is created for native OS, then the output of the print would go to the terminal of the system, the operating system. While if you run the same, remember it's the same bytecode on the runtime that is created for web browser, then the output of the print would just go to the console of the browser. So it would have a different behavior based on different runtime. Another technology is called the eBPF, and this technology is originally created to allow users to inject the customized code inside the kernel to execute some functions such as network packet filtering and do some kernel function changing, things like that. But because the kernel source code is licensed with GPL, the people would not be able to leverage the same definition of virtual machine on the other domains. But luckily, we have another project which is called UPPF, and it exactly create a user space eBPF virtual machine. And with this code, right now the people can port the code onto different spaces such as the embedded system to execute eBPF programs. And here's an example. If you're interested, you can click on the link and see people right now is exactly trying to test how it works if the eBPF virtual machine is running within the storage device. And the way they does is to build QEMU block device and embed the eBPF virtual machine code inside the QEMU block device and test it, how it works. And so right now, I just want to compare these two technologies. On one hand, both of them require virtual machine to run the bytecode generated from the browser, and also both of them support JIT compilation to ensure efficient execution. And for the eBPF program, right now we can only use restrict C to program the eBPF program, and which means when you write an eBPF program with restricted C, you can only use bounded loop. You cannot use global variable. You cannot use floating point numbers. You cannot use constants. You cannot even call functions that reside in a shared library. And it also have some strict limitation on the complexity of the program you created for the eBPF. And on the other hand, for the WebAssembly, it provides much convenient and much more flexible in terms of what kind of programming languages you can use to write the WebAssembly source code. So it supports C, C++, C#, Python, and many more. And this list is still growing. For the security model, the goal of the WebAssembly is just to provide the developer with useful primitives while protecting users from buggy and malicious codes. And so therefore, it should have much less limitation on the program in terms of what kind of things the program would be able to do. And so more recently, the WebAssembly community is trying to add more functionality to the framework, including the support of multi-processing support and the direct memory management support. And so final piece in my research plan is related to the network. And so if you still remember the diagram that I showed previously to illustrate the idea of users of storage devices, and so actually the users of storage devices are connected to a full cross-spot network. And so the performance of this idea is actually highly dependent on the efficiency of the full cross-spot network. However, to create or develop a full cross-spot network that enable a large number of endpoints to communicate with each other at the maximum speed at the same time, probably not feasible. And so therefore we may need to explore the network topology that would allow efficient communication at larger scales. And also we still need to research on some network protocol that could allow to scale within some low resource environments. And so in this context, the HTTP3 could be a good candidate because it is built on top of the UDP, and it could be much more efficient than its predecessor, which is the HTTP2, and that is built on top of the TCP/IP stack. And also the HTTP3 has solved the head of line blocking issue. And so thank you. This is my presentation. Thank you all for listening. I can take questions.
How you talk about WebAssembly and eBPF? Have you looked at all at the required resources for those environments and compared them yet, or is that part of the your research that's coming ahead of you?
It's sort of the research coming in ahead of me because this is just a plan. But I guess because the eBPF program, they have such strict requirement on the what kind of things that the program can do that I listed in this screen, and probably the performance of eBPF program could be better than the performance of WebAssembly program, I guess. Because
I have a related question. How many people in UCSC know how to program in either eBPF or WebAssembly?
This is a good question. I don't know, actually. But
so if the idea of Eusocial is that functions that are written by application programmers will be written in portable way this way, why is no work being done to educate developers?
I think this is because this kind of hurdle, as I said, the eBPF was created. So this idea was created to be used within the kernel. So if we move this idea to be used on the storage devices, maybe we may need to have a different set of limitation on that environment. So in that case, probably we could allow the program to use global reliable things like that. We kind of probably need to kind of relax some of those requirements in order to actually make use of this technology. So
let me ask you sorry, I'm interrupting. Let me ask you the same question in a different way. You mentioned about FPGAs and such. Do you think more people in the world know how to use an FPGA, or more people know how to program in eBPF?
That definitely more people knows how to program using the FPGA.
So then shouldn't we be focusing on the more popular developer-oriented technology rather than this kind of limited technology?
Well, I would back off on that because I would say that WebAssembly, there are far more people that are programming in WebAssembly than any of those, right? WebAssembly is in every browser. There are literally hundreds and hundreds of projects in WebAssembly, open source projects. And I can't speak intelligently about it because I haven't written my own programs in it, but the idea that it supports language bindings like you see here on this slide means that people already know how to program in WebAssembly, right?
That's a good point, Phil. And it sounds like it is an open replacement for Java, which is in legal disputes between Oracle and Google. So it might be the better option, but I think Jianshen was indicating that eBPF might be a better option. I was just wondering.
So in terms of the efficiency, could be some kind of trade-offs, and so the eBPF is just like emerging things. And so in order to actually understand the value of it, probably we still need some research for this technology.
Thank
you. If you're interested, I just want to interject real quick. Pankaj, there's a talk yesterday from one of our students who did a project on WebAssembly with Skyhook as an example for data processing. So that was something that we demoed, and but that was written in C, and then it's compiled with different compilers. There's one called Unscripted, but really you can write C code and it compiles it down to target WebAssembly, which is what she did in that case.
Thanks, Jeff. I'll be sure to check that out.
Then any other questions? Let me take a minute. So I guess I'm really out of time. So probably we just move to the next speaker.
Okay.
And so the next speaker would be Nidish Kamath from Kioxia, and he will be giving a talk on design constraint and consideration on computational storage devices. And he is a senior strategic marketing manager at Kioxia, and his current technology focus area including emerging interconnects such as CXL and Gen Z, and he is also a co-inventor on 21 patents. And by the way, he is also my mentor for my summer internship at Kioxia, and he has helped me a lot in exploring the design space of storage devices. And so I'm happy to have him here for the presentation. So we can bring up his recording.
Thank you for inviting me to talk about computational storage and the associated design challenges in the context of Eusocial storage. I'm Nidish Kamath, part of Kioxia's strategic marketing team, and will be presenting today's talk from the perspective of an SSD vendor. Many of these aspects are also applicable for other storage devices such as hard drives or larger storage systems. The storage industry standards body, SNIA, defines computational storage as systems or architectures that provide services related to offloading the processing of or reducing data movement to or from storage. What are the factors that drive the adoption of computational storage? First, the I/O bandwidth in a system is an expensive resource due to the limited PCIe lanes on CPUs and storage devices. Second, architectures are migrating from a one CPU fits all approach to finding the best fit processor for a given task. For example, CPUs are closest to fast DRAM in the system. SmartNICs control the point of data egress or ingress in a system, and storage devices store data on which transformations are performed. In this example, depending on the type of applications, the CPU or the SmartNIC or the SSD may each be the best candidate for performing a computing task. The next factor is the rise of edge computing. Edge devices, many of which are systems whose main purpose is to collect and store data, come with inherently small limits on power budget, mechanical size, or energy efficiency. Some examples of these systems are cameras or environmental sensors. In today's data-centric view of computing, these limitations of bringing the ever-increasing data set sizes to the CPU for processing push the storage architects and the system architects to look at scale-out architectures. By extension, this search for scaling out the architecture also means a search for opportunities of computational offload. Finally, there are physical limitations as to how fast the data can travel from the storage device to CPU cores. And this gap can only be solved by innovating in the physics of storage media or reducing the overhead of accessing the storage. I will be walking you through some of the exciting industry activities related to the last two items shown in the list. Let's first look at the system bottlenecks. The fifth version of DDR specification is now publicly announced by JEDEC and is expected to start appearing in the next generation of CPUs as early as next year. Similarly, the version 5.0 of PCIe, publicly released as of 2019, is also expected to show up in products within the next couple of years. What do all these changes or migration of the standards mean for data analysis and data storage? What both these standards do is increase the aggregate throughput of systems. DDR5, by increasing the aggregate bandwidth between the CPU and memory, and the PCIe 5.0 standard by doubling the bandwidth from CPU to storage devices. Storage devices are also getting help on another constraining factor, namely power. The familiar 2.5-inch drive, also known as U.2, is power limited to 25 watts today. These devices will eventually be phased out and will be replaced by those which conform to the EDSFF standard that allows up to 70 watts of power consumption. Every non-volatile medium, whether it is flash or other technologies such as PCM, ReRAM, or MRAM, needs a predetermined amount of energy per bit for write traffic. Hence, some portion of this increased power budget, the 70 watts, will appear as increased write performance on these storage devices. But the 70 watt limit is high enough that there will be enough power left to perform computing tasks in storage devices of the future. Next, we look at another industry dynamic, one attempting to reduce the overhead delay tacked on to transactions that access storage. Compute Express Link, also known as CXL. It's a transport layer spec that will be supported by CPUs starting with the PCIe version 5.0. It's cache coherent and brings memory-like access transactions to PCIe. Prior to CXL, the most effective way to use PCIe attached storage devices was by accessing them as block storage. In such a mode, the operating system initiates a DMA of stored data from the SSD to the pre-allocated regions in the CPU attached DRAM called page buffers. Applications would then subsequently access this paged data from the DRAM buffer. CXL allows CPUs and devices to interact as if they are peers. This peer relationship is with respect to the memory map view as seen by each device. With CXL, applications can now access addressable regions in the storage device as if those regions were a cacheable extension of the main memory. This lowers the barrier of moving data from the storage to CPU cores by a factor of up to 1000. Let's look at some of the scale-out enablers of computational storage. How does the search for scale-out or the push to scale-out architectures help computational storage? So the NVMe over Fabric standard, NVMe-OF, and NVMe over TCP was ratified in 2017, and it defines the encapsulation of NVMe commands in data packets of network protocols such as Ethernet and TCP. Traditionally, dedicated storage nodes would be built around a CPU and NIC or RNIC and connected to a set of storage devices within the same node. NVMe over Fabric and NVMe over TCP enables the remote storage clients to use these routable or switchable network protocols to access the disaggregated storage unit. Kioxia led the standardization of an Ethernet physical interface for the two form factors that I discussed earlier, the U.2 and EDSFF. As part of this ratified standard, NVMe over Fabric encapsulation and decapsulation can now be offloaded to the SSD. So system integrators can use this offloaded ability to simplify the storage node architecture. What used to require a CPU or RNIC, or at the very least a smart NIC, is now implementable using a transparent Ethernet traffic aggregator chip and the Ethernet SSDs as shown in the diagram. As an added benefit, the overhead of accessing scale-out storage is now significantly reduced in this implementation. Now we come to the most recent and exciting development in the storage world. The SNIA Computational Storage Twig, or Technical Working Group, as it's shortly referred to as, is working on defining the APIs for computational storage systems. Furthermore, some aspects of these APIs are being carried forward into defining extensions for NVMe command sets, extensions that would allow host CPU to request storage devices to perform compute tasks on the stored data and subsequently retrieve the results or status. These extensions allow efficient control flow for offloading compute tasks to storage devices and also utilize storage device bandwidth efficiently. Data transmission pipes can also couple these compute extensions with the NVMe over Fabric NCAPs discussed in the previous slide to perform offload on storage devices that are spread out across a network without being limited to the confines of a single server node. How can we leverage these developments in cross projects and research areas such as Eusocial storage and Skyhook? Gartner, which updates and publishes its qualitative view of various emerging technologies as a hype cycle curve, recently called out computational storage in its July 2020 release of the curve. As seen here, it is still early in the acceptance phase, with a lot of excitement in the technical community, but with overblown expectations among early adopting customers. This provides a rich opportunity for identifying research problems and solving them collaboratively. The first area of research that I can suggest is discovery, or the orchestration mechanisms, where the orchestrating entity in a Eusocial storage system queries the various capabilities of devices, formulates a latency and performance view of the cluster, similar to what routers would do in a network, and then uses heuristics on this formulated table to identify best offload candidates and the chain of transformation of data. Secondly, data plane transformations can be mapped from abstract APIs or object class functions to these lower level NVMe command set extensions. For example, using the NVMe compute extensions to enhance the Skyhook DM programmable object storage functions. Such mappings would allow higher level data transformation frameworks to perform the offload in an energy or bandwidth efficient fashion. With these points, I would like to conclude my talk. Thank you all for attending this session, and I'm ready to answer any questions or discuss comments that you may have about these topics. Thank you.
Great talk.
Hi, everyone. Can you hear me?
Yes.
Yes.
Yes. Yes.
So I've been answering some questions on the doc. I just wanted to see if there's any real-time questions on the call. Oh, hi, Scott.
I was going to say guilty as charged for the questions. Thank you for the feedback. A little bit near and dear to my heart. I thoroughly enjoyed these presentations over the last few years and being a part of it, and just looking forward to the success, and excited to see you called out the hype cycle effort going on, because it just further proves that this technology is on the cusp of some great success.
Yes, I agree. And I do have to make sure that the hype cycle doesn't have the negative connotation. It's just a measure of the expectations versus what the readiness of the ecosystem is to deliver.
Exactly.
So some of the, yeah.
I think the interesting part of those concepts of like the hype cycle, for those that are not familiar with that industry thing, to your point, extra add-on to what you said would be that, yes, it's early in the cycle, but look where it comes in and look where other technologies are on that. So NVMe-OF is just to the other side of the peak, for example, and it's been in progress for several years. So we can gate the timeline and the importance and the value of the technologies by using that graphic and that information. So,
Yeah, exactly. Hi, Pankaj.
Hey, I'm just thrilled you laid the case for SSD-based computational smarts, and same as Scott. I'm just glad to go after you.
Yeah,
nice way of putting the value proposition and how that combines with fabrics and other things that are going on in the SSD world. It's really well done.
Thank you.
Jeff, you have raised your hand.
Yeah, hi Nidish, thanks. That was
Hi, Jeff.
super interesting. And at the end there, Do you have a notion of, when you mentioned the pushing through arbitrary functionality or arbitrary functions rather through the NVMe interface, or do you have a notion of what, how that might look, or how would that be defined? Like, would we put library functions through there, or define new ones, or what do you have any
I
idea?
think what I mean to say is that there are, I mean, you have not only made great progress, but also have seen a big adoption of the Skyhook functionality push down, right? And I was very excited to join in on all the sessions yesterday and learn about those. But what I wanted to bring out here in this talk is that lower in the stack of a storage system would be the NVMe devices, which are coming up with these methods, not only for offloading the compute, but also being able to do so across the fabric. So you could have these computational devices sitting across the network, and you could offload compute over that transport system as well. And that ties in very nicely to Ceph, the clustered storage philosophy of Ceph, and also how Skyhook has tried to push the function offload to the clients or the OSDs, right? So, so there has to be some layer in between. I believe it could be either part of the Blue Store or Crimson, or it could be as part of the Skyhook framework itself to take advantage of these where available. So that's where I was going with. It might not mean reinventing everything. It's just how to expose these optimizations and take advantage of this at a more abstract level.
Okay, thank you.
See.
Thanks, Nidish. I think since we a little bit over time, so thanks, Nidish, and all the questions from the audience. Is what about we move forward to another speaker, and which is Pankaj Mehra, and it is a little bit different from the agenda. I'm sorry for the change, but hope it work out. So Pankaj Mehra is the VP of Product Planning at Samsung Electronics, and he was previously the VP and Senior Fellow at both SanDisk and Western Digital, and also a distinguished technologist at HP. And he has published 3 books on machine learning and systems, and also he has over 50 papers and patents resulting from his all kinds of research works. So please welcome him, and he is going to do a live presentation.
Thank you, Jianshen. I'm so glad to be in the company of Scott and Nidish. My talk will go fairly fast today because I don't want to repeat, but I do want to confirm many things that Jianshen just started to say and Nidish went over, okay? So just with a little bit of perspective from me here, okay? Can you all see my slides?
Yes.
Yes.
So this is the plan, and talk a little bit of what's going on in the world of cloud infrastructure and why this trend is so important, what we are working on. I'll cover Samsung's computational storage device, which is the Smart SSD CSD, talk about how that combines with fabrics and key value and other trends that are going on in SSD world, and leave you with some thesis topics for your consideration for the students and faculty here. Okay. So let's talk about how cloud infrastructure is built. This is a very high level view of what's going on. So you see data plane on the left, control plane on the right. Both matter because in a typical cloud data center, we have 100,000 servers, hundreds of petabytes, if not exabytes of data, sometimes exabytes in a single data lake. And we have both a very programmable, stateless service layer, and then a rich and expanding memory and storage layer. Okay, and so this words that you hear, infrastructure and ops like I and O, these words are very meaningful because we have scripted automation at a very large scale. And if it does not scale, it will fail. So in the infrastructure world, there are a couple of things going on. One is that data is the driving trend, and we don't call them computer centers anymore. We call them data centers. That should tell you something. The other thing is that, as the speakers before me also said, that driven by the amount of data, both in the compute tier and in the storage or archive tier, there is rapid evolution of memory technologies, and combined with memory becoming more and more connected, whether it's in CXL tier or in the fabric tier, smarts moving close to storage, which is the theme of the talk today. So logic wants to embed everywhere. That's what the CTO of SRC told the world last year. And persistence is getting redefined around memory technologies that are forever faster and cheaper. So, to bring it home, this idea of bit scores and fabrics, which is a memory, compute, and data center interconnects, if we marry them, what comes out of that is quite interesting. So of course, we know that bits give us by themselves memory and storage, but connected bits give us things like RDMA and some of the benefits that Nidish already outlined for you. And then bits that combine married with compute, they give you intelligent bits, they give you software-defined storage and other wonderful things in this world. And of course, pure compute gives you services and software-defined networking when combined with these ideas in other ways. If you kind of home in on storage a little bit and look at how we thought about SSDs previously, which is in terms of universal hardware concepts, and then how we could think about this in the future, it's quite interesting. So, it's not necessary that we build a storage device out of bits only. That's the primary thing that we build them out of. We have always had like a single SSD. Today has 16 ARM cores, 7 to 16 ARM cores. And a typical SSD connects over the PCI fabric, could easily connect to Ethernet. You could take those and continue to do things like control state and flow, which gives us the device as we have today, kind of a dumb device. Or we could take the same cards that we are dealt and think about them in a sort of higher abstraction that marries with things like databases like the Skyhook team is trying to do. And we get wonderful things like services, information, and the cloud. So people like us who are working on smart SSD or intelligent storage actually think in this new way about SSDs. Okay? So, the motivations for some of this work are quite clear in the data centers. If you look at the data centers that do have exabytes in them, roughly 40% of that is structured data in some form. And whatever is not structured, like photo and video, things like GPUs are rapidly converting that into structured data. So for example, at CMU, there is a project. You can walk up to a camera that is sitting and watching an intersection and say how many cars going north made a right turn between 12 p.m. and 3 p.m. today. Okay. Now you tell me that is that unstructured data or is that structured data? That's the power of GPU, is to convert what is over here, apply CNNs and other technologies, convert that into warehouse. Okay. So warehouse is a very rapidly growing tier. But some of the other speakers talked about that once we leave the data center and we look at the edge, then in recent years, much of the growth is also happening at the edge, as shown here. So the structured data, which is at the top, forms a smaller and smaller portion of the overall data that is being generated. And moving forward, we see more and more data being generated at the edge as well. So these ideas that we are starting with applying in the cloud to overcome things like roof lines and scale out sprawl, at cloud's edge, they then can be applied to remove latency, which causes frustration among users. to reduce communication costs, and monetization, right, which is advertising and other industries rely on not just capturing the content, but the context in which that content was generated. Okay, and so main things we are trying to do in the data center world and to deal with data at scale are to overcome these bottlenecks, which if not dealt with properly, like processing power and processing bandwidth not scaling with data, then get in the way of delivering performance and scale simultaneously. If we have metadata inefficiency for object storage and retrieval, then that metadata itself causes wasted endurance and wasted memory bandwidth, and even wasted CPU utilization. And some of the motivations that Nidish shared for NVMe over fabric termination, like encapsulation and decapsulation, those in the old architectures like JBoss, those things uh, are implemented using double termination. You first terminate NVMe over fabric protocol, then you terminate NVMe protocol. That causes pipeline bubbles and latency and bandwidth impact. And if you do that in a better way, then you can overcome these inefficiencies. So at Samsung, we are working on all of these. The hype cycle I have is my own creation. People like Gartner learn from people like us. So we try to lead the analysts in the industry and show them what's going on in the world of technology. So at Samsung, we've been working on computational storage for about 7 years. And personally, I come from a company called Tandem, where we used to have function offload and filter push down to DP2, which stood for disk process 2 in the mid 90s even. Okay, so computational storage is older than SSDs even. The ideas are 30, 40 years old, and databases know already how to optimize for function push down in a distributed system. And so now we are teaching them to do that to devices by making devices look like mini systems unto themselves. So in some sense, the server is becoming a heterogeneous distributed system. So the old ideas like function pushdown can apply. Likewise, my colleagues explained Ethernet SSD, and some of you know from previous work in Ceph and ROX how KV SSDs can help. So I will not revisit that. But I just want to point out something to you, that these ideas that existed at system and software level for over 25 years are now coming into the SSD. And that's the reason why we are revisiting these 25-year-old ideas in 2020, is that what it took an array or a huge system with boxes, some CPU and some memory and some SSD and networking, that's what it took to implement these ideas. And now we can implement them in each SSD for much better scaling of this kind of capability with the amount of data. Okay, so I will not dwell into all the ideas. Focus on smart SSD, which delivers application awareness, acceleration, and offload. By keeping data inside the SSD and still computing with it, it also saves on L2 to memory bandwidth and system data bandwidth. So in the future, what might happen, these ideas might combine and we may get things that look like smart SSD and Ethernet SSD, so things like eSmart, and this is driven by overall trend in the data center. Okay, so the Samsung Smart SSD incorporates a Xilinx FPGA next to every 4 terabytes of data. So the left half of the little cartoon I have of the Samsung Smart SSD computational storage device looks exactly like a traditional SSD. It has a very low power, very low cost controller that, unlike some other people do computational storage, they try to do controller functions in the accelerator. We already have really fast ASICs that handle this, and we have them at low cost built in our own foundry. So there is no need to reinvent that wheel. We make a high-speed connection to an accelerator and give it its own memory. As a company that makes both NAND and DRAM, this is easy for us to do. Package it all together and make it available in a U.2 form factor 25-watt device that has 3 and 6 gigabytes a second internal bandwidth, has about 500,000 LUTs of FPGA, with the idea that the traditional bottleneck in the system as you add drives after 4 or 8 drives in a system, a typical 2-socket server starts to bottleneck. We have seen this in database and media processing with real customers. The idea of the smart SSD is that we want to bulldoze past that roof line and do that at a higher slope because of internal bandwidth and internal compute that scales with the amount of data. We've been doing this smart SSD work for a couple of years now, and many companies have now ported to their accelerations to the Samsung Smart SSD. For example, company BigStream, which accelerates Spark SQL and Kafka and other workloads, has this trace from a real query on TPCH benchmark, where if you would have executed that query in traditional way, you would have pulled all that data out of the SSD. You would have applied decompression and then filtering to that data and applied downstream SQL processing like joins and group bys and so on. And if instead you use the smart SSD, you first get to filter the Parquet data, then you transfer reduced data to the host. And even if you don't accelerate that downstream processing, you still see the 2 to 3x benefit in performance. And if you do accelerate that downstream processing, such as joins and shuffles, then you will see even more benefit approaching closer to 10x. We have done this work with the company whose meeting technology we are using today, Zoom, together with a startup company from China called CTXL. They have ported their FPGA computational video processor to the smart SSD's FPGA. And using transcodings to process, for example, meeting recording that will be generated today. A 2-socket server would peak out at about 768 frames per second at 720 video with very high CPU utilization, as shown in the red here. Instead, if you use the smart SSD, 3 smart SSDs can do more of that work than a 2-socket server. And as you build a server with more and more smart SSDs, you can do the work that is 10 times a 2-socket server. We have worked with a startup company called Idaticom, likewise on storage service use cases, to build compression, inline compression, both at file system and kernel level, and with similar results. Okay. So besides Spark, we are working with other companies on Postgres, and we have engagements around MySQL, Cassandra, and all the major databases in the world. Okay. And companies like Swarm64, for example, are public with the release of software that supports the smart SSD. Okay. Cloud data centers are now adding a new class of nodes because of the existence of smart SSD. These live between the traditional compute nodes, which are stateless and have typical single-digit terabytes of data. Storage nodes, which are heavy and cheap and sometimes have HDDs in them. These have typically about 400 terabytes of data. So applying standard principles of memory hierarchy, you can imagine that there would be a tier in between that would have tens of terabytes of data. So this tier can be either connected over a data center fabric or could be a WAN connection to, for example, Amazon S3 or Microsoft Azure Blob Storage. In this tier, the data is in a computational storage friendly form where it goes from typically columnar compressed format here to typically row-wise format here, such as CSV or other native format of the database where it can be filtered and projected efficiently. And previously, this used to be done with separate FPGAs and SSDs. Increasingly, the architecture of accelerated cache nodes in the data center, such as you can read about in various cloud architecture conferences, is now moving towards this linear scaling with a unit of scaling that is a computational storage device. We've also been working on other use cases. For example, a large government customer has worked with yet another partner company that took their regular expression IP and ported that to the smart SSD's FPGA. A single server with 24 smart SSDs can scan very complex regular expressions at about 60 gigabytes a second per server. That is unheard of. You can see the smart SSD's performance in the red here. And by comparison, the CPU-based system not only performs lower in terms of overall throughput, it actually has a very choppy and poor QoS performance, okay? Which means unpredictable query times. Okay? So the smart SSD is out there, it's delivering its benefit. I just want to tell you what's in the smart SSD, but this is not the only way the smart SSD is used. Like I said, one part of it looks exactly like an SSD and exposes a physical function on PCI bus that you can program using NVMe protocol. So you can do standard NVMe read-write operations. You can build block storage, object storage, or file systems in a standard way. The other part of it looks like just like an FPGA. So if you know how to use an FPGA card by itself, your IPs, like I showed in the previous slide, people have easily ported, sometimes in a matter of weeks, their existing FPGA IP to the smart SSD. Okay, so it presents just like a standard Xilinx FPGA, a data physical function and a management physical function for privileged operations, such as installing IPs. Working with Xilinx, we programmed a 3-port PCI switch, which then enables all 6 kinds of connections between the 3 things that need to be connected to each other, which is the host, the SSD part, and the accelerator part. And when you move data from the SSD to the accelerator, it uses the private data path. So this is where it's taking advantage of internal bandwidth and scaling of compute and bandwidth with the data. The memory resources that are attached to the FPGA are also visible on the PCI bar exposed by the device. So you can do a standard OpenCL based allocation and deallocation into the SSD. And I have some slides now that will go into a little bit of coding example with that. Okay? So what we are doing is we are in the process of transferring our learnings from this device into the SNIA working group. We have worked closely with customers such as Alibaba and Zoom. Alibaba at last year's Flash Memory Summit actually embraced the Smart SSD's blueprint and called it AliFlash V5. We are delighted that they did that. And moving forward, we are working with the Storage Networking Industry Association and NVMe Technical Working Group to standardize best practices that we have developed using Smart SSD. Like I said, the Smart SSD to software people exposes a very familiar tool chain stack. So you can either program Smart SSD using standard Vivado tools, or you can program at a higher level using OpenCL or other abstractions. Okay, and some people are writing their own middleware and their own stacks. Some people are writing their own shells for the Smart SSD, not using the Xilinx shell. Okay, so all kinds of work is going on at all different levels to access the Smart SSD, either in host-based direct way or indirect way, or to do IPs that take advantage of it at device level. Okay, so Smart SSD, for example, for Vivado RTL developers, you can use standard XOCC command, and it is supported out of the box by Xilinx tools since their 2019.2 release. So you can just have a standard RTL target that you can compile for. Okay. The coding is also very simple. Like I said, you can use OpenCL commands like CL create buffer to create a buffer in the FPGA's DRAM. And then you can map that buffer and just do standard read-write operations using NVMe commands under the hood or NVMe commands directly. And then you can trigger the IP that's on the FPGA using OpenCL commands such as CL and QTAS. And then you can read the results back. Okay, it's pretty simple. Sometimes the code changes are just less than 10 lines of code in a typical application. Okay, so we are using the Smart SSD to improve in data center in 2 ways. One is something called east-west scaling, which is for things like Spark. Clusters that are based on Smart SSDs do the work of 3 times as many nodes. So fewer nodes are used, therefore cost is less. And clusters that are closer to the edge are using the Smart SSD to do something called north-south scaling. So instead of having separate servers to do transcoding and object detection and this kind of media operation, you can use a single Smart SSD-based server to collapse the work of many server types into one. This reduces server-to-server latency, which is a key element of even live streaming today. So believe it or not, a storage technology like Smart SSD actually has a place in both improving real-time and offline operations through this idea of north-south scaling. So I promised you I'll end with some things for you to read and some things for you to do. So, you know, we've been working with SSDs as their dumb devices. Therefore, when we aggregate a bunch of these devices in a chassis, our methods of doing things like RAID and erasure coding are also designed for failure of dumb devices. When you have abstractions like Jianshen pointed out, you know, which combine both compute and data, you have to think in new ways. How will you do data protection and compute protection in the age when data and compute are co-resident in a common abstraction, like MBWU? So I want you to look at some work that has gone on in the cloud for dealing with unreliable nodes. For example, at Stanford, Mert Pilancy has been working on polar coded matrix multiplication to deal with drop rate of servers, which can be as high as 5% if you're using cheap servers in the cloud, okay? Or from 10 years ago, you can read Martin Abadi's work on computing with compressed and encoded data, which is now you know, embedded in best practices in databases. Optimization and orchestration and data placement are also good areas to understand. Here you can read some work from UCLA, for example, Professor Chang's students, Zhenwan Ron at UCLA has been working on something called Insider, has a good initial paper that will give you some ideas. And from many years ago at UT Austin, Mesam Lavasani did his PhD thesis on data flow-based orchestration for this kind of devices. I myself have worked with our SVP, Namsung Kim, who came from University of Illinois, where he was professor. And we put out an initial position paper at DAC in 2019 that talks about that if you convert devices into little subsystems, how you can use familiar distributed system concepts and abstractions to optimize for these devices. Let me stop here and give you some time back. So that's my pitch. And if you have any comments or questions, I welcome that. Are you all still here?
So any questions from the audience? I may have a basic question. So
Yeah.
Samsung SSD use FPGA, but some other computational storage devices use ARM cores. Can you give me like a little bit comparison, like what, when and why, and in what situation we choose what kind of computation resources within the storage devices?
It's a good question. You know, for us, this is not a choice of either or, but both and. Okay. So I want to point out to you that I don't want to make a false choice. And an FPGA can be used to implement processors. Indeed, if you read Professor Andrew Chen's work at University of Chicago, they use FPGA to build UAP, which is a processor that is layered on top of the FPGA. Okay. So the first generation smart SSD that we had built used Xilinx Zinc SoCs rather than Kintex FPGAs and had built an ARM cores. And we may go back to that architecture in a future smart SSD, okay? So we have been looking at the balance of doing the soft overlays versus having hardened cores. When we first put out our device, there was no users. Commercial, see, this is the difference between academia and sort of prototype oriented work on acceleration versus commercial grade acceleration. When the Zinc SoC was out there with ARM cores, there was no commercial IPs to take advantage of the ARM cores, whereas there were tons of IPs to take advantage of the FPGA. So our customers demanded that we do an all-LUT implementation, okay? Now, you know, because of the work of NGD that Scott and other people can talk about with you, okay? People have understood that cores can also be used for offload and acceleration, okay? So future devices will actually employ a combination of hardened and soft acceleration, okay? Maybe Scott, you want to add something to that?
Sure, and I would like to highlight that we actually use the exact same Xilinx FPGAs for our 15, 16, 17 development work. The reason for that example, the combination of an FPGA with an NVMe controller that Samsung has today is a great way to do prototyping work and efforts like that. Our ability to want to kind of get into the commercialization efforts of it, we went forward with designing an ASIC solution. The primary reason was the target market. So as has been highlighted by both of the previous presenters, Edge represents a great opportunity, and the new form factors like the EDSFF that Nidish showed have a challenge of combining those two architectures into that type of form factor. You need something in a more of an integrated solution. That's why we've chosen to go to an ASIC already. Does it hinder some aspects of the application, especially from an academia perspective, where, for example, both of them have referenced what's going on in SNIA and NVMe? It could challenge our efforts moving forward, but in the meantime, we have the opportunity to kind of be in the front forward of that kind of effort and help, you know, turn another ASIC kind of thing versus just roll RTL code, but it's always trade-offs.
Yeah, we are working with some like ARM and RISC-V type IP providers to say, can you take your architecture and put it on our FPGA? And then based on the outcomes, we may go with one or the other in the future, or maybe a third type yet. Okay. So I think, you know, this industry is still evolving, and the Smart SSD is already 2 years old. So at the time when we made it, this was the right choice. Okay, and it is still applicable. It is still, we are finding commercial applications like I showed you, and government and you know, research institutes like genomics and other organizations are also looking at it. So we built what was most applicable at the time, and then as we move forward, we are looking to combine the architecture trends that are coming from both sides. Okay.
Thank you. Thank you.
Okay. Thank you everyone for listening.
Any other questions?
I think a good answer to your question too, Jianshen, will come from Jason as he gets ready to present, because he's coming from that IP point of view more so than necessarily the end product. So I'm actually looking forward to seeing what he has to say.
Thank you for Pankaj Mehra's great presentation. So right now we move to the next speaker, who is Jason Molgaard, who is from and he will be giving a talk on flexible computational storage architectures, and he is a principal storage solution architect, and he is recent focus, of course, on computational storage as well, and he is very experienced in ASIC SoC design, and he has proven architecture design, verification, and design leadership experience with an emphasis on developing enterprise storage and server ASIC. And please welcome him. So we can play his.
Hello, everyone. My name is Jason Molgaard, and I'm a Principal Storage Solutions Architect at ARM. I'm here to speak today about flexible computational storage architectures. So quick agenda. Let's take a look at the drivers behind computational storage, then delve into the details of controller architectures with Linux, look at some key workloads, and then wrap up. So what are the drivers behind computational storage? So one of the big reasons is bandwidth. With ever-increasing drive capacities, there's lots of data to be processed. So why move that data to the server when it can be processed right on the drive itself? This translates into a power savings, and that, of course, equates to a cost savings as well. There's a latency benefit with computational storage. You don't have to spend the time moving the data from the drive to the host CPU for compute. This improves reliability, just fewer moving parts, so to speak. And then it plays a role in security as well, because you don't have unencrypted data leaving the drive. So just to level set, what is computational storage? So if we take a look at these diagrams here, let me turn on my laser pointer. So we have this diagram here on the left that's kind of a traditional model SSD that would make a request from, a server would make a request to the storage. The storage would move the data to the compute. The server would perform the computations and then optionally move results back to the storage. With computational storage, the server makes a request to the storage itself performs the compute, and then results are returned to the server. This provides all of the benefits of energy efficiency, low latency, and security that I previously mentioned, but it also allows data-centric workloads to be deployed directly to the drive based upon the type of data that's stored on the drive. So the Storage Networking Industry Association Computational Storage Technical Working Group is working on a standard. This group was formed almost 2 years ago. ARM joined and helped found that organization. There are 45 participating companies today with about 211 representatives. There is a draft standard that's available publicly. You're welcome to go download it and take a look at what's been developed so far. And essentially, this technical working group is focused on a couple of different areas, both the hardware architecture, what are the definitions, what does an architecture look like for computational storage, but also software libraries and APIs, so that everybody has kind of a common interface for how to determine what computational storage capabilities exist in a product, how to deploy them, how to use them, and just a overall standard from that perspective, so everybody's on the same playing field. So now let's get into the details of controller architectures with Linux. So if we look at a traditional SSD, it already has a significant amount of compute. So this block diagram here on the right is our SSD, and it's kind of broken up into a front end and a back end. That's kind of how typical controllers are developed, where the front end usually has host interface management and the flash translation layer management. The back end is typically the flash management for managing the flash channels. Of course, there's a significant amount of hardware accelerators built into that controller, encryption, LDPC, compression, all sorts of different things. And certainly a very large component in an SSD is the DRAM, and that certainly, if we try to draw that to correspond here in this picture, to the tune of 1 GB per terabyte of flash that's in the SSD. So today we're seeing drive capacities of 16, 32, 64 terabytes, and that likely translates into a 16, 32, and 64 gigabytes of DRAM in that drive, a significant amount of DRAM. So this drive, this traditional SSD, already has a significant amount of autonomous processing on the drive. So the host today sends LBAs, logical block addresses, to the drive, and the drive converts those to physical addresses for where the data is actually stored on the media. The drive also stores the file system that the host uses to map files to LBAs. So if you have a drive, a computational storage drive, with Linux running on the drive, now the drive is capable of not only mounting that file system and recognizing the files, but can then convert those LBAs into the physical addresses needed to actually find the data on the drive. And of course, it can now perform any compute operation that was previously run on the host. You can do it either in real time as the data is streaming in or out, or after the fact by pulling the data out of the drive media and performing operations on it in place. So why Linux? Other than the benefit I already mentioned about being able to mount the file system, which is certainly a big one, why have Linux at all? Well, certainly I think we can agree Linux is quite ubiquitous. There are standard versions, tiny versions, huge open source developer community. It's very, very prevalent, very ubiquitous. So Linux is going to work with whatever computational storage drive standards come out of the SNIA technical working group. There won't really need to be any changes whatsoever for that Linux support. Workloads can be deployed to the drive using standard tools that are readily available, like Docker or Kubernetes. And security is a solved problem on Linux. It's well understood and will certainly contribute to ensuring that our computational storage drive is secure as well. There's a vast ecosystem of ported and optimized software for running on Linux. So all the standard administration tools, containerization, protocols like TCP/IP, NVMe, databases, machine learning, all this is readily available and quite supported on Linux. So let's take a look at options to add on Drive Linux. So if we take a look at these diagrams over here on the right-hand side, starting with this one on the top, this this box that I'm kind of circling with my laser pointer, this is a traditional SSD where we have our front end that we mentioned previously and our back end, a PCIe interface. And this is a daughter card or an interposer that would connect up to it. And on this daughter card is an applications processor. Data can be moved from the drive across this PCIe interface into the applications processor for compute, and results can certainly be sent back. So this is a great proof of concept for computational storage, leveraging existing SSDs today with a small little daughter card, but it has some challenges. Certainly one big challenge is the fact that there's a back-to-back PCIe interface. So we're not saving any of the bandwidth that I had mentioned previously. We still have to package the user data up in NVMe, in PCIe, move it across this interface, unpackage it at the other end, perform the computation. Certainly that takes a lot of bandwidth, power, time, and doesn't really solve any of the latency challenges. This applications processor also requires its own non-volatile memory storage to boot the Linux, and likely its own DRAM. So to solve a lot of those challenges, we need to take a look at this middle box here. So this box here is our same SSD with the front end and the back end processor. But now we've incorporated that applications processor into the same controller as the rest of the SSD functionality. We've eliminated the back-to-back PCIe interfaces, so that saves all that bandwidth of moving the data back and forth. This applications processor is now able to share the same DRAM as the rest of the SSD controller, and of course can share the same non-volatile storage, the flash media itself, for storing the Linux. So this is great. Lots of existing products today, or several existing products today, based upon this kind of architecture. The next logical progression then is, well, why not combine the applications processor and the front end processor into one cluster? And that's exactly what this diagram here on the bottom is showing, where the applications and front end processors have been combined. And of course, this provides additional area benefit, cost savings for the controller itself, which just lowers the overall product cost. So taking a look at Linux, one recent version of Linux, the Debian 9 version, has these system requirements. So 128 megabytes of RAM minimum, 512 recommended, and 2 gigabytes of storage. So this is actually very small, all things considered, when compared with the SSD itself, less than 5% of the storage. If we take a typical 16 terabyte SSD with 16 gigabytes of DRAM, we're using less than 5% of that for the Linux operation. And of course, we've got 16 terabytes of storage, so using 2 gigabytes is also quite small in the grand scheme of the overall storage capacity. So kind of extrapolating a little bit, if we look at this picture here on the left, we essentially have our controller with 4 real-time cores showing, and that traditional SSD takes all of the data that's stored on the media, sends it across to the host, and the host does the processing. With computational storage, over here on the right-hand side, we want to be able to take the controller and allocate some of the cores for doing computation right on the data. Of course, we still need to be able to send all the data to the host if necessary, but we want to extract the insight right from the data, find what we're looking for, or perform the operation, and just send the results, send the insight to the host CPU. So taking that a step further, we want to even have flexibility to change the balance of that workload over time. So perhaps during very peak times of the day, when the drive is especially busy, maybe there's 0 cores or 1 core at most allocated to performing compute of the data that's stored on the drive, and the rest of the cores are purposed for managing the transfers in and out of the drive. But later on, during off-peak times, we can repurpose some of those cores to running Linux and performing the compute on the drive within the same controller. And so if we kind of step back and say, what have we created? I would suggest we've really just created a low-cost edge server. If we look at this picture over here on the right-hand side, it's an edge server with an SSD connected to it. So here's our edge server. So this PCIe, CPU, DRAM, and a network interface. And then this PCIe flash CPU DRAM, that's our SSD. Well, we've now deployed on those CPUs Linux. We can substitute a TCP/IP interface for the PCIe and running Linux on that drive and use NVMe over fabrics to speak to the outside world. And we've effectively created this, where we've got our flash media, our CPU, and our DRAM speaking across a network interface. It's essentially a very low cost, small edge server. So computational storage scales and collaborates very nicely, especially as more capacity is added to systems. So looking at this little picture here on the left, we've got 4 computational storage drives, each of course with its own compute, offloading this host CPU. If we find that that's no longer enough capacity and we need to double our storage capacity, shown over here, now we have 8 drives, we've doubled our compute in those drives. And all these drives are capable of working in parallel on a particular workload to offload this host. So work can be getting done on all these drives at the exact same time in order to get tasks done as fast as possible. So one of the things that we're in the process of investigating in ARM is a Hadoop cluster with those types of computational storage drives, and what would the software stack look like? What would the overall architecture look like? So here's kind of a slide that speaks to our thoughts and what we've been working on. I don't really have any results to share today, but when we do, I'll be happy to give an update on that at a future time. So let's take a look at the key workloads. So there's lots of workloads listed here, and we can come up with lots of different examples. So offload, compression, encryption, encoding are certainly some very obvious and key workloads. Database acceleration is another one. You know, if you've got this very large database of information, whatever that information may be, why move all that information from the database to the server in order to perform a query and search? Content delivery network is another great example where maybe you've got your movies that you want to stream to various devices, and on the drive itself, you can re-encode the data at various bit rates in order to for the different size screens that users are using to view that content. Image classification is a great one for computational storage, running machine learning type workloads to look for images or types of patterns in images. Transportation with lots of telemetry data in airplanes, for example, and high definition map data for autonomous vehicles moving forward. So lots of applications for computational storage. So to kind of conclude, computational storage is happening today. The SNIA, the technical working group, computational storage technical working group, is developing a standard to deploy and manage workloads. Linux, we believe it delivers the fastest route for workload development, deployment, management, because everything is ported and just works. And compute scales as drives are added. Each computational storage drive that you add allows more cores to work in parallel. Thank you.
All right, any questions from the audience? So I may have one question. So I'm quite interested in the Hadoop experiment you're showing on the slides, and just wondering why you choose Hadoop in favor of the other distributed storage system, for example, like Ceph. I know because I'm familiar with that. But Ceph provides you an opportunity to offload some function like COX class. You can push down some function onto the data nodes, and so that you can probably do more experiment. Yeah.
So great question. No real great reason probably to answer that. I think that we have some knowledge and some experience with Hadoop internally, so that's kind of why it was selected. I think we're just as interested in Ceph. and we'd happily do something with Ceph as well, given adequate time and resources. So maybe that will be kind of a future task moving forward.
We should talk after my presentation.
Okay. Definitely. Sounds good.
Hi, Jason. Great
Hi,
talk.
Nidish.
I had a question about the on-drive Linux. I mean, you chose the particular distribution to illustrate the small footprint, right? The small memory footprint. One of the things the SSD maker has to be wary of is that the access to the stored media should not suffer from a denial of service attack because of the offload. So do you think a regular Linux distro would be a good fit, or is there room for putting in an RTOS or something with a more hard real-time constraints in there?
I think, sorry, I didn't mean to interrupt. Go ahead.
No worries, go ahead.
I think RTOS is certainly, something could be done with an RTOS. I'm not going to say it can't. The nice thing, of course, about Linux, as I mentioned, is the fact that it recognizes the file system. If you have something with an RTOS, unless it's has the ability to mount a file system, that challenge is still there to find the files so that you can actually then send the LBAs that you want to operate on. But as I had mentioned in the slides, I think that security is kind of a problem that's been thought about already from a Linux perspective, and certainly it isn't it's something that needs constant attention. Security isn't just one time done and it's over. There's always new challenges related to that, but it's something that certainly gets a lot of attention in Linux and is understood. So that I think is going to help. Certainly, we've opened up a new attack surface on a drive that we didn't have before, because now we do have this Linux. Now we have a TCP/IP connection potentially directly into the drive down the road. So there's a lot of work to be done there, and I don't have all the answers today. I wish I did. The SNIA technical working group, this is an area that we're wanting to focus on, and it just hasn't gotten as far along yet as we'd like. And the plan there isn't to invent a new wheel in terms of security. It's more to point to existing security standards that are well adopted, well understood, and successful so that we're all using things that are proven and not inventing things that are potentially vulnerable.
Got it. Thank you.
Yeah.
Scott, do you have any questions?
No, I was just potentially going to comment related to the fact that Nidish made a very solid comment that read and write have to stay priority in an environment. And so those are certainly some of the things we had to look through when we built our architecture, was how to ensure that read and write do not get countermanded by trying to do some kind of compute. And to your point, RTOS is very useful. You do have that working to manage the right amount of resources between the host and the host controller and the applications controller within the device. And in our particular instance, as I've presented at this conference before, we actually use a clustered file system to help file lock and things like that. So.
Any other questions? Let me check the minute. Seems like no other people have questions. So what about we move to our last speaker, Philip Kufeldt. Thanks. So first, thank you, Jason, for his great presentation. And
thank you, everyone, for having me. It was really a pleasure to be here today.
Thank you. And our last speaker, Philip Kufeldt, is from Seagate, and he will be giving a talk on application of computational storage research and specifically would focus on how to augment Ceph to make use of computational storage devices. And he is a senior technologist in Seagate Research Data Flow Group, and he is also the current chair of the Cross Industry Advisor Board. And he has many years working on the computational storage devices space, and so we can expect we can learn a lot from him. So, and also he has been working with me through Cross for a long time in the past, and so many thanks to him. So let's bring up his video.
Good morning. My name is Philip Kufeldt, and I am a technologist inside Seagate's Research and Development Group. Today, my talk is going to be on the application of computational storage. It's a primary focus of my research, and I'm going to be focused on Ceph during this talk. Let me give you a little bit of background. I've been building computational storage devices since 2015. Back then we chose to use key value as the initial fixed function in these devices, namely kinetic. So we called them kinetic drives, but they were functionally computational storage devices that did key value as a fixed function. While I was at Toshiba, the kinetic drive we demonstrated also did a programmable function as well. We embedded Ceph inside the device. But the problem wasn't creating the devices and the software. The problem was showing the value to existing systems. We had this nice new device, but no software, no mainline software used the kinetic protocol. So showing the value was very difficult without a fairly big, sizable integration effort. So consequently, kinetic kind of faded off into the background, but Seagate has continued to do research with kinetic and has continued to improve and utilize kinetic in our research group. My research is focused on exactly that question. I want to be able to essentially ask a testable assertion of, is an offloaded version of an existing software platform better than the baseline? For my research, I'm targeting Ceph, and I'm specifically examining whether or not offloading key value, because Ceph uses key value extensively inside the OSD. Both BlueStory uses key values for both metadata and data. And if we offload those, is there a benefit? Examining programmable function offload as well as part of my research. A little bit of background here. I think we've seen these pictures before in the past. This is the Ceph architectural overview. Ceph is a collection of OSD servers that essentially manage the disk drives and provide I/O operations to those drives. There's a series of monitors that maintain membership of the cluster. Above is a client tier that uses various interfaces into Ceph, such as a block or a file or S3 interface. All of those interfaces are implemented using Rados, which is an underlying object API. Some of the problems that we're focusing on this research is that a fixed server ratio, that once I define an OSD server, the number of OSDs that it manages remains the same unless there's been drive failures, but I can never expand it. I can only reduce it. And finally, the blast radius, that if I lose an OSD server, I lose all of the media that's attached to it, which can be terabytes in terms of hard drives. That means that all that needs to be re-replicated or re-erasure coded when it's complete, when that failure is recovered. My research is kind of broken up into two phases. I'm going to look at essentially offloading key value first, which has the added benefit of disaggregating the drives. So how am I going to do that? I'm first going to essentially containerize the OSDs, which has already been done. It's available on the network, and I will just leverage that. But then replacing the direct attached storage with computational storage service key value drives, which are essentially network accessible. This allows the OSDs to be scheduled anywhere inside the cluster because they access their local storage via a network protocol and not a SATA or NVMe link. This means that we get to get rid of the entire OSD tier of servers. That means that I have a flexible server storage ratio. It's really a question of how many OSDs do I schedule on a container server, and I can change that dynamically. Blast radius is reduced down to a single drive. because if a container server goes down, I just reschedule those containers on other servers. Phase 2 is where we take those containers and we basically move them back to the drives themselves. And now we have OSD drives completely encapsulating Ceph inside the drive itself, which allows the sellable cycles in the container servers to be reused and used for other purposes. But we're not going to focus on phase 2 in this talk. We're going to focus on phase 1, and that work is ongoing, and we're going to talk about that now. To essentially integrate in a key value network drive into Ceph, I'm going to have to modify the object storage daemon itself. This is kind of a high-level block diagram of some of the code that's inside an OSD. You know, you have the Rados API layers on top, which accept the I/O requests from their clients, and also interact with other OSDs inside the cluster. There's the object methods. These are the extensional object classes that Skyhook uses to define new functionality as part of the access methods. That's all done at that level. There's durability. This is where replication, erasure coding via OSD to OSD operations. But in the back end is the actual object store itself. This is the unit of code that manages the drive and knows how to essentially break up objects, store them on the drive, and retrieve them from the drive as requested. The object store itself is really a class that you can implement different providers of the object store. And right now the choices are Blue Store, which is the default. This is what everybody uses today. In the past, it was File Store. That was the legacy object store that was built on top of file system technology. There's also Mem Store, which is really more of a performance tool. It's a non-volatile object store, or it's a volatile object store, excuse me. K-Store, which is an experimental one that uses key value to store and retrieve its data. So that's what we're focusing on this research, is that we're essentially using the K-Store implementation. And inside K-Store, they implement another object class called key value DB, which abstracts the K-Store away from individual key value database implementations. With this class, I can essentially bring up a K-Store on top of RocksDB, LevelDB, Memcache, or Kinetic. So again, in this resource, I'm focusing in on utilizing the Kinetic store. This code is all available as experimental features. Some of this code is no longer available in the latest releases. It's been cleaned up because the Kinetic code hasn't been used in so long, but it's still available in the Nautilus release, and that's what I'm using for my research. I have brought up all of this code, and I actually have Ceph OSDs that are running on top of Kinetic right now, and I'm beginning to do the performance analysis and have already found issues that I'm resolving. Let's do a quick Kinetic key value refresher. It's an authenticated TCP/IP protocol. It can use SSL or not. It has end-to-end checksums to provide data integrity. It has ACL controlled accesses, allows you to segregate the key space and permit controlled access to various parts of the key space. It has sync and async APIs, and it has cache control that allows write through, write back operations, as well as being able to flush and control the cache. It implements an in-order key value database, specifically as a log structured merge tree, which provides basic key value operations such as get, put, and delete. Because it's an in-order key value database, it also has range operations that allow you to do get next. So I can iterate through keys by just getting the next key or getting the previous key. I can also get the list of keys in a key range by issuing a get range call. It has transactional operations as well, compare and swap via put that allows you to do an atomic guaranteed atomic put as long as that data hasn't changed since the last time you looked at it. It also has a compare and delete via delete as well. It has a batch operations that allow you to group up puts and deletes into a batch, and either all of the operations complete or none of them do. It has peer-to-peer operations that allow you to do kinetic drive to kinetic drive operations. So I can say, put this drive locally, but also put it on this drive and this drive as a single command to a kinetic drive. And of course, it has various media and security management operations. One of the things we found initially as we got the Ceph cluster up and running, we saw big performance problems. We started to do the analysis, and immediately one of the biggest offenders was our own, Seagate's own kinetic client. And we were using the C++ client, and it had some pretty significant problems that we felt like the only way to remedy was to rewrite the library. And we felt also that this would provide us a nice performant backend that we could then port to Python, Java, and a bunch of other places to provide differing language bindings. It's broken up as a research tool to allow us to test against various different protocol versions of the kinetic protocol. It also has differing backends, because one of the things that's changed over the last 5 years is that the access APIs to the network stack has changed over the last 5 years. You know, we have legacy kernel sockets, but we also now have DPTK, you know, some zero copy things in the form of kernel splice. We have IOU ring. We have SmartNICs, and we even have new protocols such as Quick. So we felt like if we put some flexibility in the back end of this library, it would allow us as a research tool to test the various different backends to see, you know, what better performance we get from the differing backends. This was brought up this summer, and we're in the process of testing it right now. One of the things that we noticed as we were doing that kinetic library is that it would be fairly easy to add a exec call for programmable functions, which I think is a necessary piece for computational storage, is to allow general purpose functions to be inserted in the drive and exec inside the drive. How this would work is that you would essentially build your function into a shared object, and then store that shared object into a key value pair on the drive itself. And then there would be an exec call that would be added to the protocol that would accept a function key, and then either a key range or a key list as operands to that function, and possibly some random parameters that the function can define itself for its operation. Once that exec call comes in, it would access the objects locally, run the function against those objects, and generate a result key value pair that would be returned as a part of the result. But it also would be left around so that you could do a get on that key later on if you wanted to return to the results of that operation. We're initially going to implement this with the user Berkeley packet filter, and we're looking to Skyhook for input, because we see this as an interesting feature to take some of that arrow functionality and push it down to the drive and have it run locally. Performance testing. We need a tool to do performance testing because we need to be able to test our different kinetic libraries and prove that we did a good job. We also need to diagnose server performance issues, which means running a benchmark on the drive without the network there to isolate the actual kinetic server. So we need a lightweight tool. YCSB is sort of the tool of choice, but it's very heavy. It usually sits on top of large software stacks, and consequently, it being heavy really isn't noticed. But it's Java-based. Test case definition requires Java programming, so it really doesn't fit for our needs to run in a restricted environment. RocksDB is tied to the Rocks API. It's not interesting. Samsung hit the same problem, implemented KV Bench. It definitely has more flexibility in defining test cases, but it's still limited. It also is tied to the SNIA object API, which is another layer to go through, which we'd have to port to our drive. So I've opted to look at FIO and implementing an FIO engine that essentially utilizes the standard read-write and test case methodology, mapping that to get, put, and delete. I'm doing some tricks with using the offset to define a key. That trick requires us to load the key value data set before running the benchmark, which is very common in key value. YCSB has to do the same thing. And we're also providing with the FIO the variable key size to test, 16 byte keys versus 128 byte keys, for example. But the basic code is done. I'm debugging it now, and I might extend FIO for better KV testing. what does the hardware look like? I only have a few more minutes left. It's essentially the hardware we're using right now is what we call an interposer card. It's a small PCB that slides onto the front of a hard drive. So it connects via SATA to a hard drive, but then on the other side of the card, it's providing dual 2.5 gigabit Ethernet via the connector. It has an SoC, DDR, and network support on the card. And it plugs into a 4U enclosure that has 96 drive slots. Each of the drive slots are compliant to SFF 8639 and 9639. They support 2.5 gigabit to each slot, so they're dual redundant Ethernets to every slot. And it has redundant 240 gigabit per second uplinks to the top of rack switch. So this provides us with the hardware we need to do the testing. And then with that hardware, we have implemented Ceph clusters that allow us to do comparative testing. Of course, we'll use FIO on the drive itself to make sure that the libraries and the server that's inside the HDD are performant. But when it comes to comparing it for the ultimate goal of comparing baseline Ceph with offloaded Ceph, we need to do this in a Ceph environment. So basically created a cluster that allows us to define different OSDs with different object stores. So we have a blue store, a K store with RocksDB, and a K store with Kinetic. And then we've implemented RBDs on top of that, and allows us to do RBD testing that go through each of the individual paths independently. And we've done that through various crush rules and pools. Final thing is I want to thank Aldrin Montana. He was my intern this summer, and we were able to get the Kinetic C library written this summer. He was fantastic, and I really appreciated all his help. And he's going to continue to work with me in the fall. So I'm really looking forward to the rest of the fall with him. That's it for my talk. If you have any questions, let me know. You can always contact me, and we can talk about this offline as well. Thank you. One thing I would like to add is that all of this stuff we consider as open source right now. You know, any of the things that we're doing with FIO or Kinetic, the Kinetic libraries, even the Ceph work is all open source, and we're willing to you know, collaborate with anybody on this research if anybody's interested.
Thanks, Philip. Very interesting and great work. And this work is pretty aligned with my research. I will also spend my part of my research on the applying Ceph on the embedded storage device and see how they perform. But maybe I will specifically focus on how to optimize the resource consumption of Ceph in various domains.
Yeah, I think that's phase 2 is heavily dependent on that work, and I'm looking to you to see what you find out and what you discover. I think when you start looking at putting software-defined storage management inside a drive, like Eusocial is pointed at, that currently the current implementations are all fairly heavy with regard to resources, and that may change with the addition of Crimson, but it's not clear that they're going to be using Crimson with hard drives, right? It might only be with SSDs.
The other thing I'm quite interested in is that you have the concept of using the key value interface to push down the function to the storage devices, and is that the case? I'm thinking about, what if we want to apply a couple of functions onto the same set of key value pair before the result returned back to the clients? And the motivation is that probably some of the function could be used as a shared library, and in that case, that shared function could be like factor out onto a different library. And so in that case, if the shared library doesn't exist, then how does the error comes back to the clients?
So I'm not sure I understand the question. You're asking whether or not the embedded function can operate on multiple key values at the same time?
The same multiple function operate on a same set of objects.
Oh, on the same set of objects. To me, that's a programming issue, right? That there has to be infrastructure that allows that kind of locking and mutual exclusion, right? I mean, it's the same thing as if I had multiple programs accessing the same file up at Linux. If the programming model doesn't provide the kind of mechanisms you need to do that, then you can't do that.
Any other questions from the audience?
Hi, Philip. Nidish here.
Hi.
A quick question about the interaction between the Blue Store and the K Store. Sorry, the Blue Store and the Kinetic. So the Blue Store itself has key value acceleration and the indexing. Is that an additional level of indirection on top of the Kinetic interface, or how do you do that?
So first of all, I've chosen not to use Blue Store at all, and that's for several reasons. First of all, there was already code inside the tree, which was outside of Blue Store that already supported key value. Secondarily, it also makes it a nice kind of protected development environment that if we do show value and we show that this is actually a good thing, pushing that into the tree is going to be a lot easier than if I had modified Blue Store, because Blue Store right now is the mainline code base. Blue Store is also very complicated, and it was a little bit daunting to figure out how in the right places to sort of cut out RocksDB. Obvious, pretty easy to cut that out. But when you start talking about the blob store inside Blue Store, you know, where it actually stores the values as sequential blobs in the device, it was far less clear how easy that task was going to be. So I think moving over to K-Store, which is equivalent to Blue Store, separate code, but they both implement the object store class, and you only pick one object store per OSD. When you configure an OSD, you say that this is going to be a Blue Store OSD, it's going to be a K-Store OSD. And you only have one provider running at any given time. Gave me that distinction away from Blue Store and also gave me a much simpler code base. I think the difference in code size is pretty dramatic too. I think the K-Store code right now is, you know, measured in like less than 10,000 lines of code, and I think the Blue Store code is well over 50. Far more complicated of a piece of software. So right now, there's the downside to that selection means that nobody has really looked at or tuned the K-Store code, right? It's always been an experimental feature and it hasn't gone very far. So although my focus right now is getting the efficient interface with Kinetic to the OSD, my feeling is that I will be doing mainline K-Store code changes as well, especially because I think there are features in Kinetic that we can take advantage of. For example, a lot of the I/O operations in K-Store are batch operations where they will essentially collect up a bunch of writes in a transaction, writes and deletes, and essentially do them as a batch, but they have to do all the batch management themselves. Whereas with Kinetic, they can just hand it off to the device and let the device deal with it. Some of the other areas are around iteration. They separate like OData and OMAP data from each other by prefixing keys with characters that allow them to create key spaces for OMAP data and OData, right? And you can then do key range operations that grab you only the OMAP data, for example, OMAP keys, and then they iterate through them. Providing an iterator that runs on the drive, you know, becomes a very interesting thing. That if they could define that function, pass it down, and then do the iteration on the drive, it's another big saving. So I think the selection of KStore is good for a couple of reasons, but it also has some downside in that I've got a lot of general KStore improvements to do, as well as just integrating with Kinetic.
Got it. And do you see this kind of the iterator being pushed to the drive would also have some benefit for the traditional file systems that you would see on Linux hosts in terms of all the metadata management for the file system?
I don't know. I mean, there's really no file systems that use key value right now. Everything is block based. So it's not clear to me that they could take direct. I mean, that was some of the problem with Kinetic, right? Is that a lot of the mainline storage use cases were, completely tied to the block model. And to do the integration and retrofit of a key value API was very difficult. And as everybody looked at that work, that's why the interest kind of waned away from Kinetic back then. So not sure, without looking at how you might do one of those integration efforts, whether or not there would be an advantage or not. But I definitely see, I mean, there are other places where iterators make a lot of sense, right? With RocksDB and other things of that nature.
Yeah, certainly. Thanks.
Other questions?